Thanks for the introduction, and thanks to the organisers for this wonderful conference with all these great people here. As it says, I'm actually dual affiliation at the moment. I spend most of my time in Warsaw, but I'm also still affiliated with the University of Durham and Jeremy Hudson's group there. And this talk is mostly talking about work that's done in that context. So, just a very brief outline. I'm going to talk a bit about motivation, not motivation for ultracold molecules. If you're not motivated about that, you might be in the wrong conference. Just a very brief overview of the theory. I won't go into too much depth, don't worry. And then talk about some of the ways we've applied this theory to experiments, including some of these rubidium plus calcium fluoride experiments that Mike's just talked about. So there'll be a bit of overlap there. I'll then talk about some work we've done recently, trying to extend this to more complicated interactions, and then have some conclusions. And just as a note, I know this is a laser cooling conference, but to a theorist, there's less difference between laser cooling and association. So I'll draw on some examples of these alkali dimers as well. So why collisions? Oh, we've lost all the stuff in that picture. So there are a number of different things we want to use collisions for. Many of them have been mentioned already. One of the top ones, even if you're not interested in collisions in themselves, you often want to do collisional cooling to get even lower than the temperatures you can get to with laser cooling. Ultimately, if you're hoping to get to any kind of condensate, you probably need to care about the scattering length. And this is an example. This is an atomic example, but it's from the top of my to-read list of controlling scattering lengths. And Mike just mentioned at the end of his talk, I mean, maybe we want to be able to do association, and you need to understand the collisions in that context. There are also some fundamentally molecular things, and we've had these mentioned as well, the sticky collisions and reactive processes and all these things. So hopefully there are some reasons to care about collisions. However, with collisions comes a potential for loss. It's just a small subset of the loss for different systems, different contexts, but things are going to be faster or slower, but your molecules are going to be lost in collisions. That's what experience has told us in most cases. You might recognize some of these figures. As we said, there are many different ways you can have loss. Already mentioned reactive, rotational, and spin relaxation. In Mike's talk, Mike also gave a good example that even elastic collisions can cause loss in the wrong circumstances. And I'm not going to say anything about sticky collisions, but I think we're going to hear a bit more about those in the next talk. Loss is occasionally the topic of study, and one of the best examples is Cancquen's wonderful experiments looking at product state distributions. But usually it's just something we want to go away so we can keep the molecules that you've spent so much time and effort making. But for the purposes of this talk, we're not going to distinguish between how the molecules are going to get lost. They're just, something's going to happen when two molecules come together, and it's complicated, and we're not going to specify. So I'm just going to talk about loss, mostly. So in terms of scattering, in atom-atom systems, we can do an awful lot of calculations in a lot of detail. We've got very good models. Atom molecule is very hard. This basically comes down to the size of the basis sets that we need to describe this enormous anisotropy. This is 7,000 wave numbers of anisotropy. With lithium calcium hydride, the masses are so small, we might be able to do this. But if you go to something heavier, rubidium calcium fluoride, the masses are much bigger. And I'm not going to say it's impossible, but I'm not doing it anytime soon. And there's also the issue of the potential. We don't have accurate enough potentials to be predictive. So anything we do, even if we can do a full calculation, you need to see how the results vary over potentials. That means you have to do your calculations 100, 1,000 times over. So full calculations, for the purpose of this talk, full calculations are out of the picture. They're not things we can reasonably do in a reasonable time scale for the systems we want to understand. And this means we have to get approximate methods. So this is just a sort of a cartoon sketch of how I think about quantum defect theory. To me, there are two parts. One is that you simplify the long range to the simplest possible model that you can, get rid of everything you can, and then you get rid of the short range entirely and put some parameter there just to represent what's going on there. And you say, I'm not going to worry about the details, but there's something going on there. So this is just in a cartoon form. Yes. And so we're going to start, for the systems of interest, or the first place we're going to start, as Mike said, is we're going to start with this long range r to the minus 6 potential. It's going to be, this is relevant for a lot of systems of interest, not everything, but most atom-atom interactions and even molecule-molecule interactions, if you don't have a polarizing electric field, a dipole-dipole interaction comes out as r to the minus 6 in the effective potentials. So this is the most important single potential for ultracold scattering. And we will come back to this molecule-molecule in an electric field. So this, a lot of numbers here, but this is just setting down some parameters that we're going to be talking about. And so to parameterize the short range, we turn to two parameters. One of these is a phase parameter. You actually often see in the literature people use the scattering length for this. You should think of scattering length as an asymptotic long-range property, but it serves to parameterize the short-range phase. We just use the short-range phase directly, and there's a simple tan relationship between them. So when you see this delta of S, just think this corresponds to a scattering length. We also have to parameterize the loss, and we use this Y parameter of Idiatic-Julienne, which runs from no loss at Y equals 0 to the so-called universal loss. I want to draw your attention to this, that people think about this Y, but the probability of being lost isn't actually quite this Y. It's 4y over 1 plus y squared. So even these quite small y values, so y equals 0.25 corresponds to 2/3 loss. So the scale is a little skewed. So I just want you to bear that in mind when we're talking about these y values. Because there are good theoretical reasons why this y was chosen, but it does distort the scales a little. Anyone theoretically inclined can think about this short-range S matrix, but if you don't want to, you don't have to. And this is just to link this back to the Idiatic and Julienne work. This is modeling KRB plus KRB loss. That work looked at the leading low-energy terms. Our work extends this to higher energies and higher partial waves. So we're building on this work and extending it to broader ranges of applicability. So just briefly on the theory of this, the main body of the calculation is actually calculating reflection and transmission coefficients. Don't ask how it's done. You can read the papers if you want. I wouldn't recommend it. I'm simplifying a bit here. The two reflection coefficients aren't the same. The two transmission coefficients aren't quite the same. But this is conceptually right. And so we can have this representation of the scattering process in a very physically intuitive manner, where we have a reflection off the long-range potential, and then we can tunnel through the long-range potential and have sequential reflections in a short-range region before tunneling back out. So this is a very physically intuitive representation of the scattering, I think. And this is very naturally applicable to some kind of absorbing or lossy process at short range. And this shows up a resonance condition that when there's sequential reflection, when the total phase, the total magnitude you get through that process is 1, that's when you get resonance condition. It's a very intuitive picture. And so you see that when the reflection of the long-range potential drops from 1, you lose the resonance condition, and when the magnitude of this S drops from 1, so when you have loss, you also lose a resonance condition. And so just shows some fairly brief, pure QDT results. Nice pretty pictures. One of the advantages of a cheap calculation is I can do these nice big pretty pictures. 1 million points is quite cheap. The broad structure is here at low energy is the S-wave structure, and we've got a polar infinite scattering length here and a 0 scattering length here. And then we've got these features from higher partial waves. This is for the elastic cross-section with no loss. Just to say that the regular spacing of these shape resonances, this is because we've used the same boundary condition for all partial waves. That seems like a quite severe approximation, but it's better than you think. Even in molecular systems, we think, although it's quite hard to get an exact beat on how good or bad it is. Looking now at the inelastic loss, the low loss, again, this feature is dominated by this broad S-wave feature and then higher partial waves. But as we increase the amount of loss to 5%, then 25%, these wash out very quickly. And so at y equals 0.25, you can sort of see there's a lump for this P wave, and if you look very carefully, there's something for the D wave, but it's quite hard to see. And then at y equals 1, there's no feature in the phase because it doesn't matter what phase 0 is. So now I'm going to talk about some of our applications of this to various experimental systems. I'm going to tackle Mike's results in the opposite order. I'm going to talk about the MOT first at higher temperature, at about 2 millikelvin. Don't worry about the experimental details. So this is what the theory looks like. This now has delta on the y-axis and y on the x-axis, and there's nothing going on. So at 2 millikelvin, these results are really dull. There's not an awful lot to learn here. There's no feature in delta S. There's nothing quantum going on. It's all just being averaged out by thermal averaging and partial wave averaging. It actually agrees with a completely classical model of the collision. And as Mike said, we attribute this to fast rotational loss. We then move on to the other set of results that Mike talked about in the magnetic trap. And now we see a lot more structure as a function of this delta S. So we've now got some quantum features of this. We've got interference effects. Just to say a bit more about this, this feature here is actually a P wave. This ridge down here is really a P wave feature. It's a P wave shaped resonance that's coming out at this temperature. There is a bit of an S wave feature, but it's mostly washed out by this point. So we have something coming up here. It's not sort of fully quantum, but we're still a long, long way from the single partial wave regime. But we're seeing something that the model is picking up. We can't really assign the parameters fully yet, but the combination of this and the MOT results already allow us to sort of rule out some of these parameters. We can fairly confidently say that we don't have this P wave shape resonance in this system, and that's not saying what we do have, but it's giving us significant information about the scattering in this system from a really quite a simple model and a simple set of results. And the other point is just that this is the spin relaxation, and Mike talked about that already, that's just very slow. For the third example, I'm now going to go to the bialkalis. This is rubidium cesium plus rubidium cesium results. These are from Simon Cornish's group in Durham. I should have put up a reference, but never mind. And in this measurement, they showed quite convincingly that these are two-body collisions, despite these being in the absolute ground states and there being no two-body pathways out. So these are the collisions that are attributed to sticky collisions and thought to be the result of laser-induced loss. But we just consider it loss in a generalized sense. And now we see we've got a lot more structure. We've got these, and we've actually got a much lower loss parameter here. So it's all limited to 0.4 or lower at this temperature. But this doesn't give us or it doesn't give us much hint where we lie on this delta S parameter. However, they also did the experiment at a number of different temperatures between about 0.8 microkelvin and 4 microkelvin. So we can use this and look at the temperature variation to narrow down our parameter space even more. So if we're near resonant, if we've got a large SY scattering length, and then we predict this very characteristic explosion of the loss rate as you decrease temperature, for example, which we clearly don't have. So this actually allows us to narrow down the parameters really quite a lot. And we actually get to fit y to 0.26 and fit delta to this value just above 0.5 pi. And as I said before, delta has this relationship with the scattering length. And so this fit implies that there's this scattering length of rubidium cesium plus rubidium cesium collisions. I guess it's an open question how much you truly believe that or what you think that parameter means, but there's something in the physics that has some characteristic of a scattering length of between about 200 and 300 Bohr. There's something in the physics that this model is picking up and representing like that. And so that's about as far as we can get with this single channel model. So I've got about 8 minutes left. So we now need to think about what sorts of things we can, or how we can go beyond this simple model. Everything I've talked about so far is done with very simple, pure single channel, pure R to the -6, long range. Of course, real systems don't have that for a number of cases. Perhaps the most immediately applicable is a dipole-dipole with something polarizing it, but anything else. And so we need to use some numerical solutions here. Left out a lot of theory, but we've figured out how to do this, and we've implemented these methods, and we can now get these R&T parameters that are central to the theory I described earlier. Before we got them just from analytic solutions, we've implemented getting these from numerical solutions with essentially any potential, any interaction, any coupling scheme you want. And that means we can go back to all the systems we've done in the past 20 years on Ultracold and redo them with these absorbing boundary conditions if there's an interest. There isn't for most of them, but there may be for some. And the way we've got it set up is we do the expensive part of the calculation once, and then we can apply as many boundary conditions as we want for. It's not quite 3, but it's about 3 matrix inversions. And so this is quite recent work, so we looked for the first test case of interest. So we're actually going to look at electric field shielding. So just a very, very, very brief orientation if you're not familiar with electric field shielding. This is a series of energy levels for pairs of dipolar molecules. This is KRB in this case. So this, for example, this red line is 2 molecules in the first rotational excited state. And this these energies cross with ones coming down from that have one molecule in the ground rotational excited state and one molecule in the second excited rotational state. And there's a dipole coupling between these. So near this coupling, this is just a blow up of this region here. Near this coupling, or near these crossings, the two states will repel each other as the dipole-dipole turns on. And this will give you a strongly repulsive potential in the upper state. And this is proposed for static electric field shielding. And it will work with any dipolar diatomic molecule. You'll just rescale the axes. And this was demonstrated fairly recently for KRB. And the idea is if you can have a repulsive potential, you stop the molecules getting to short range, and you have shielding, and you allow them to cool without allowing any of the complicated lossy processes that happen at short range. So these are our calculations for this KRB at this crossing point of about 12.3. We have this resonant feature. This red is the elastic, and the blue is the total loss. And so we have, on this side, we've got a factor of, I think it's about 7 between the elastic cross-section and the loss cross-section. These results are actually very similar to some older work from Gourvin-Caminair. But we've also gone beyond this, and we've just changed the parameters in the boundary condition. So this is now quite a small loss parameter for various different phase shifts. And we now have a whole load of structure. These results just came in the past 2 weeks, so we don't understand exactly what's going on here. The series of resonances, these might be related to the field link states that have been proposed for molecules. We're not sure. We've not investigated fully yet. There are also some effects we don't really understand in sort of these background loss rates. There's sort of an order of magnitude difference here. Again, there's a lot for us to understand. We don't really know how best to use this new toy that we've just got. So we're working on that, and we're looking for. We have many ideas what we can do with it, but we're still looking for more. The final thing we did is we applied this to calcium fluoride, and where we got a factor of about 7 shielding in KRB, now this factor is, what's that, 6 orders of magnitude. These fields are higher because of the rotational constants in calcium fluoride, but this shielding looks very promising for calcium fluoride and hopefully other laser coolable molecules. Again, we haven't done an awful lot with this. These are results that just came in the past 2 weeks. Okay, so some conclusions. We've used this QDT model to get very efficient modeling and calculation of loss in relevant systems. We applied it to a couple of different cases, and once we get down to, we can see quantum interference effects even by 100 microkelvin. And once we get down to 1 microkelvin, we can really get quite a lot of information out of these things. Once we've extended these methods, we hope to be able to do many, many more systems and do more things of interest. Shielding is our first goal, but will be other things, I'm sure. I need to give some acknowledgements, particularly to Ruth and Bijit, who have been doing a lot of the actual work on these recent results. Ruth has brought the code and the implementation of these methods has made it all work. And Bijit's the one that's been doing on the calculations on shielding. So this is a Darwin group, and this is the Mikhail Thomson group in Warsaw that I'm also a member of. It's quite a small audience, but we do have a postdoc position available if anyone is looking for a theory postdoc. And I'd also like to take this opportunity to advertise a workshop on ultracold molecules that we're running in Warsaw in September next year. Okay.
Thanks, Matt. Yeah, John?
Yeah. So the calculations you did on CAF do look very promising. This is essentially long range. So, but can you think of any reason why this wouldn't apply in the same way to complex polyatomic molecule?
The question, I think, comes down to the structure and the Stark effects, because this is essentially a degeneracy in sort of in the Stark dress states. So that's the key thing. So if the polyatomic molecule has a structure and a Stark structure that's very similar to these diatomic molecules, it will all behave just the same. If it's different, maybe they'll be shielding at a different point. I don't see a reason it would be impossible. Yeah.
What is the reason of the 6th order of magnitude versus a factor of 7 compared?
We're still working through this. We think it's mostly to do with the rotational constant, and that the larger rotational constant just means that the states are more separated for an equivalent coupling strength. So we think it's essentially a rotational constant thing.
But for larger rotational constants, the field also goes higher?
Yes, that's certainly true.
So that is a trade-off still, right?
Yes, yes. The field is also dependent on the dipole moment. So you get some of that back with calcium fluoride because you've got a bigger dipole moment than in KRB. That's, yes.
Maybe to help answer Ken's question, why is there any inelastic process left at all? Why doesn't it just go to zero? Is it because there's tunneling through the barrier?
Yes. I mean, you're never going to turn it off completely. And we're also including loss going out to other long-range states. Oh. Yeah. So what I was going to say is that you can have inelastic coupling that's happening outside the barrier to the corresponding state. So it's not clear that even if you didn't have tunneling, it's not clear that you would get the loss down to zero.
So we got time for one more.
No, it's up to you.
Go on, Emma.
Yeah, maybe it's a very naive question. So I was wondering, since Mike's talked on this 2D collisional tool, the theoretical integrations of about this 100 microkelvin thing like that. I was wondering how exactly do I interpret the data? Because, I mean, in the experiment, we only measure the rate, right? So how do I know, how do I pinpoint where exactly is my data on this tool?
From a single measurement, you can't really. So anywhere along this black line would give the same result at this temperature for this system. As I said, for the rubidium cesium, once you include the temperature dependence, then you've got more discrimination, and we can actually do quite a good fit once we've got this temperature dependence over a factor of 5 or something.
Thank you. So I guess kind of piling on to my original question, I'm curious of what would happen if you were working with parity doublet states, like lambda doublets. Do you have any thoughts on that?
Not immediately. I agree, that's a very good question.
Okay, well, you can think about that.
Yes.